Welcome to class 50. We'll start with a problem, then we'll move to different parts one by one. Let me start with an example, important example. This is important because this is the only problem we'll do from ARMA PQ. If you remember, we found autocorrelations of problems, whatever examples I must have given you, we found autocorrelations. Even we left partial autocorrelations. In today's class, I will find autocorrelations, partial autocorrelations as well. Both the things we will find, and we will try to know what are partial autocorrelations and autocorrelations with examples. But let's do a problem. This will be the first and last problem. Whatever problems, examples you must have seen before. Now, in today's class, we'll do a problem where you will see ARMA 1-1 process. ARMA 1-1 process. Okay. And this one, xt is equal to alpha xt minus 1 plus et plus beta et minus 1. They've given the direct question in the exam also many times. But more than that, you should be able to know how to find autocorrelations in case of ARMA 1-1. Although these days, if you are pursuing data science or any other course, you don't need to find autocorrelations. The concept is important because we have R coding and Python coding you can use and you can get in seconds. It's quite easy. So, frankly speaking, they know a little bit of time series. Actually, what you know, the students from statistics and actual science, they know that is in depth. The students from data science, they know a lot of coding, but yeah, they are struggling with all this. But yeah, the coding helps. Without knowing anything, you just produce a lot of graphs. So how to find here row 1? Okay, we'll start with gamma naught. Remember, we use Walker equations whenever we found autocorrelation for ARP process. And also when you find autocorrelations for MA process, you must have done separately. Okay, you have to do it separately when you are finding autocorrelations for MA process. Normally what we do is, when you find autocorrelation of MA process, you write this one in terms of whatever you have in the right hand side, also this one in terms of whatever you have in the right hand side. Suppose I have written this question, whatever there we have to write here in MA process, and whatever there, all three terms we have to write here. 3 terms here, 3 terms here. And individually you have to find, you have to check this one with this one correlation, the first term, okay? This one with this one correlation, this one with this one correlation. Similarly, you take the second term. Also you do the same thing, correlation, 3 terms, third term. That way we do in MA process. In AR process, how we do? We use Walker equations, or we try to put the value for one of such. Okay, we don't put the values for both. Now coming to ARMA process, it will normally be like AR way. Okay, whatever way we find the autocorrelation for AR process, we do similar way. However, there is a little bit difference. That means we have to see the correlations. Suppose I will write gamma naught here. That will be covariance xt minus 1 plus et plus beta et minus 1. Okay, these are the autocovariances. Now we'll see one by one. Remember, these are the autocovariances. We have terms covariance alpha xt minus 1, xt minus 1. So alpha xt minus 1 xt minus 1, that will be gamma naught, the same, right? And the second one et xt minus 1 plus, let me write covariance et xt minus 1 plus the third term beta et minus 1 xt minus 1, beta covariance et minus 1 xt minus 1. Don't you think this is like xtet, covariance of xtet, whatever it is? Let me write here. If I write xt minus 1 and then I will see et minus 1 here, you find xt minus 1 from here, it will be alpha xt minus 2 plus et minus 1 plus beta et minus 2. If you write this one and then see the correlation with covariance with et minus 1, it's here, okay? So that will be sigma square. So that will be sigma square. This will be sigma square. I will replace this by sigma square. Sigma square you got from this relation. This is here, okay? So if you see these two correlation, you will get sigma square, because always xtet there is a correlation, you get this one. So when you write this one with et minus 1, then what will happen? This one you will get 0, okay? et to t minus 2, et minus 1, that is 0. They are uncorrelated uncorrelated values, white noise process. And et minus 1, et minus 1, there will be a link, okay? That is covariance of et minus 1, et minus 1, that is variance of et minus 1, that is variance of et as well, that is sigma square. Remember, et follows normal 0 sigma square, we say. Even if you write et minus 1 also, that will be normal 0 sigma square. Et minus 2 also normal 0 sigma square. With this assumption, we are doing the whole time series. In econometrics, if you do, you will have lot. We consider E1, E2, E3 with different sigma square. That is heteroscedasticity. We are not doing that here. Let's not worry. So at least in our course, we have constant variance. So we got extra term here. Now see the second one, covariance et with xt minus 1. If you put xt minus 1 here, you have to check whether you are getting et or not. Suppose I write xt minus 1 here. Then what will happen? T minus 2, et minus 1, you will get this way. So with et of xt minus 1 or not, et, where is et? Et minus 2, that will be 0. et minus 1, that will be 0. Uncorrelated errors, okay? And you will never get et from xt minus 2. Even if you write once again xt minus 2, you will not get et with xt minus 2. This is past one, okay? So we will not worry about the middle term. Safely we can ignore the middle term, okay? So that you will have your original, so that you will have only two terms for this, beta sigma square, remember. So this is beta sigma square. Now if you find 2 here, you check here xt minus 1, xt minus 2. We'll write something for that. Then xt minus 1, et with xt minus 2. In xt minus 2 expansion, if you write here, once you can check, you will never get et, okay? So again nothing you will get, because et is the white noise for today, and this one is 0 anyway. T minus 2, T minus 1, it's T minus 2, it's T minus 1. So now there won't be any problem. Gamma 3 it will be alpha gamma 2, and you can proceed further. You will not get these terms again. So you can write finally gamma t or gamma k, whatever way you want to write, after this term, after second term. It becomes easier. So you can write gamma k is equal to alpha k gamma 1. Check here. Alpha 2 will be alpha gamma 1. Okay. How about gamma 3? Gamma 3 will be alpha square gamma 1. If you put back, you will get it. Don't worry. Okay. You continue putting here, you will get this way. Whatever it is. If you divide by gamma naught, then here also if you divide by gamma naught, you will get rho 2 from autocovariance to autocorrelations. So you will get all autocorrelations afterwards. Will not worry about all those. Now, the only time it will take when you do it, when you find gamma naught. This brings a little bit of complexity. Let's see what is gamma naught here. Okay. So if I write gamma naught here, then I will start with this one, the first term. Okay. Covariance alpha xt minus 1 with xt. And then we'll see the second one, et with xt. Let me write et with xt. Now you can see et with xt. Where is et? Here is et. Et minus 1. See, the problem is when I write covariance et xt, it becomes easier if you are dealing with a MA1 or AR1, even pure AR processes. But yeah, these terms you should be careful. If I write this one here et, and let me write xt value here, alpha xt minus 1 plus et plus beta et minus 1. See, in this case, this and this 0, safely you can say. This and this sigma square, that's fine. Sigma square we have. Plus, we have another one, alpha covariance xt minus 1 et. Xt minus 1 et. You go on checking before writing anything in ARMA processes. Do you have xt minus 1 et covariance? You try here, xt minus 1. You will get xt minus 1, et minus 1, et minus 2. Still you are not getting. Okay. So, in these processes you are supposed to check. Okay. Let me write properly how it was. Sorry. Xt minus 1 was here, right? Xt minus 1, et plus beta et minus 1. Okay. How about the third term? Beta et minus 1, xt minus 3. So, in alpha, we did this one, second one, right? So, let's do the first one, covariance xt minus 1 xt. So, when you write covariance, let me write one by one here, alpha, and this one will come anyway. The first dependency, xt minus 1 xt, that is 1. This you will get anyway, the first one, alpha sigma 1. And other terms, for other terms you need to think always in any AR process or ARMA process you find. Okay. So alpha gamma 1 will be there all the time. And we got sigma square also. Let me write sigma square. Plus, see here we got two terms. and from this term onwards you will get one term. The only term you need to see is the first one. You have to check properly in ARMA process. Otherwise, these becomes easier after 2 term onwards. Now, let's find this one. And till now, whatever we have done, I don't think there should have been any problem. But yeah, here you have to look carefully. When you find this term, let me write the term covariance, the third one, plus beta covariance et minus 1 xt. So this is, see, et minus 1 xt means what? This is t minus 1, this is t. This is process. This is et minus 1. You can say that they are independent, but when you write this way, t minus 1 here, t here, when you talk about the process here xt, okay, today's random shock will not depend on previous values. Whenever I started the last class or what was the problem on that day, okay, whatever is the problem today, when I give you 5 minutes more or I will teach 3 minutes less, the random one, the white noise means the whatever the innovations or the fluctuations happen today, that is no impact. That will never dependent on the past value. That is what I am saying. But the opposite you can say, the converse is not true. We are not checking this now. We are checking et with xt minus 1. There is a confusion all the time. Et with xt minus 1. Not this et with xt minus 1. Okay. We are checking et minus 1 with xt. Sorry, et minus 1 with xt. We are checking. So here in the third term, we are checking et with xt minus 1. Let me write et with xt minus 1. This one. Et with xt minus 1. Okay. Et with xt minus 1. That is covariance et. You have to write xt minus 1 once again in the open form, xt minus 1 here. So the first term will be alpha xt minus 2 plus this one will be et minus 1. There is nothing between et minus 1, that's fine. And the third term beta et minus 1. Okay. This is et. So let me write one by one. Et minus 1, the first one. First one, there is 100% surety you will not get anything. Okay, that's for sure. Now you can try with alpha t, alpha et, that is sigma square anyway. And then we'll check et with alpha xt minus 2. Okay, one by one. If you check bt.
Sir, should it be et minus 1 and beta et minus 2?
Which one?
Sir, covariance of et comma xt minus 1.
Okay. I was right. I saw the other equation. Okay. This is et minus 1, right? And this is t minus 2. Because we have to find this value from this one by changing t to t minus 1. So we have to change everywhere. So you change everywhere. Yeah, this is fine. So now we'll do one by one. Et with alpha xt minus 2. Okay. If you put xt minus 2, will you get et anywhere? Et minus 1, that will be 1 anyway. So what is et minus 2? Which term I have written here? Covariance of ET xt, covariance of xt minus 1 xt, then beta covariance ET, where is the term covariance of ET? Because still we will get terms here, two terms, like two terms are here in gamma 1, gamma naught, three terms you will get, okay, three terms. So I've written covariance ET xt. Let me check once here where I got this. Beta, here I've written gamma naught, and here I put xt. I kept xt and I put here xt minus 1 alpha, yeah, I've taken here. Then et with beta et minus 1, yeah, et minus 1 xt, this is correct. Et minus 1 xt, yeah, this is et minus 1 xt, right? I've done differently here, right? That's why I'm not getting. See, don't you think it will be this one I'm considering? Please confirm here, because lot of things are happening here, so I'm a bit absent-minded. Beta et minus 1 xt we are finding, right? See, the first one, xt minus 1 xt, et xt we have written already here, these two. The third one is beta et minus 1 xt, okay? Here also I have written beta et1 minus xt. So let me write. Beta, anyway it's there, will not worry. Let me write beta. This one I have to find, et minus 1 xt, et minus 1 xt. Normally in AR or MA we have a particular procedure we follow, okay? You need not think more than that. But here, because we have ARMA process, you have to think deep. So when I write et minus 1 and write 1 by 1 term here, alpha xt minus 1. See here, we have et minus 1 xt minus 1, we got it. Like we got here also, sigma square, here also you will get 1. Plus the second one will be covariance et minus 1 and xt. Here, in xt we have written the first term, you have to write the second term, et. Safely you can say this is 0, because we have only the errors here, et minus 1, and then beta is there though, plus beta et minus 1 and xt minus 1. Okay, this alpha xt minus 1, this is there. So et minus 1 we found with the first one of xt, okay, and the last one also you have to write xt term. So here you will get 1 for sure, et minus 1, et minus, that is beta sigma square, you got here also, okay, let me write that one, beta sigma square. So here you get beta sigma square. Plus here also if you find, this will not give you anything. Here also you will find 1 sigma square, xt minus 1, et minus 1. You can check this way, xt minus 1, et minus 1. Okay, if I write xt minus 1, I will see whether I will get et minus 1 or not. See, we have 1 here, okay. So that way you will get another sigma square. So alpha sigma square, alpha is here, alpha sigma square, okay. So this is your gamma naught, this is gamma 1, this is gamma 2, this is gamma 3. So only you need to think when you are finding gamma naught in ARMA process. And remember, this is the only one problem, you need to think for 5 minutes, okay, that's all. So even if students solve, I have seen in classroom sessions, okay, so they struggle to do it. Once you have to do it before the exam, even it comes in the exam, it might create problems, okay. Now let me leave this one. Now let's talk about partial autocorrelation. I will show you that one from the actual table also today. Whatever formula I derived, this the autocorrelations. Okay, we found autocovariances. Then you can find autocorrelations. I will show you that one. Wait. Now when we talk about partial autocorrelation, this is something you need to know conceptually. That's all. We don't need to know it. We don't need to know it in details because the derivations are not actually included. Some points were there before, but now there is nothing. So we'll not worry about those. You just remember something. If you remember something, then that will be quite all right. Okay. Now what is partial autocorrelation? It's like this. Suppose I'll start with this one. Let me write AR1 process. AR1 process. In AR1 process, when I write xt is equal to alpha xt minus 1, alpha xt minus 1 plus CT. This is a simple AR1 process. What will happen? If you see this one here, let me write the timeline. I have the timeline. Yes, I have the timeline. Okay, but yeah, that might not help. So let me insert one here. Okay, how I've written. I don't need that. This is the timeline. Okay. Now you consider the points. Okay, this is t, this is t, this is t minus 1. So if you see this relation, AR1 relation, we say that t has a strong relation with t minus 1. Okay, how strong it is, alpha will determine. Forget about the innovation or white noise, whatever you say, ET part. It's like this, xt is alpha xt minus 1. What will happen? If I write successive points here, I go back here, I say that there is a link between t to t minus 1. If you say alpha 2, forget about et for the time being, alpha 2, you start with 10, it will go this way. Don't you think it will become stationary? Never. How it's increasing? If you take alpha half, 0.5 or 1 by 3, it will decrease. Okay, then we'll talk about stationarity and all that. If alpha more less than 1, again I am not going to that. But if you see the dependency, the value at t is strongly dependent on value at 1. Not only that, what I am saying, not only that, when I write xt minus 1 here, I will get this alpha xt minus 2 plus et minus 1. Then when I write once again xt and xt minus 1 value, I will write here alpha xt minus 2 plus et minus 1. Then what will happen? Then again I will see that there is a link, though if I take alpha 0.2 or 0.3 when it's stationary. Okay, so 0.3 means 3 divided by 10. Okay, or maybe if I take 0.1, that is 1 divided by 10, it will be 1 divided by 100. Okay, but there is a link. That's what I am saying, xt minus 2 plus alpha et minus 1 plus et. So if you see t and t minus 2, there is a correlation. There is a correlation between t and t minus 2 as well. So if you see directly AR1, you can say that there is no correlation between T and T minus 2. That is wrong. You can say that there is no correlation between T to T minus 2. Although this is AR1, we have correlation between T and T minus 2. So we'll have rho 1 here, that is between rho 1 comes from gamma 1. When you talk about gamma 1, covariance xt minus 1, that is there, and this is Markov process because this depends only on the last term. AR1 process is Markov, okay, but AR2 process, when I write, it's not Markov because it depends on the last two steps. Also there is a question, although AR2 is not Markov, it can be changed to a Markov process. We'll do that later, okay. If you have time today, we can do today this one as well. This is not Markov, but this can be transferred to a Markov process because there is two-step dependency. Now coming to AR1, when we say this is Markov, it doesn't mean that it will not depend on this. T value will not depend on this. When we say Markov, we use the information at time T minus 1. We don't have directly T minus 1 here. But indirectly, you have link between T to T minus 2 through T minus 1. Okay. So if I am A, I don't know C, but through B I can go to C. Through B I can go to C. That is what I am saying. So when I say correlation, there is a correlation between A to C. It's not that there is no correlation between A to C, but there is a through medium. What is the direct correlation between A and C? If you see the LinkedIn profiles, they show. Maybe you have not, okay, maybe you have something, I can say, but if it's cut up between there is no connection, then that will be 0. So direct correlation between A to C and through correlation, how can you separate that? Through correlation and direct correlation, everyone will be included finally. That's what I've written this way. Suppose I'll give you one example. That is partial autocorrelation. Partial autocorrelation means direct autocorrelation, and you can only estimate using statistical techniques. You can know, you can find, okay. See this one. In rainy days, in rainy season, suppose today you have this much rain. I mean today if you see, and there is a place like this where the waters they get accumulated. Suppose up to this you have water, and we have rains. It's raining since last 3 days heavily, okay. So if you see this much water, it's not that this much water, whatever water we have, this water is due to today, okay. You have some yesterday also, okay, some from 2 days before and some from today. Not everything is from today. So when you see this relation and you find rho 1 or gamma 1, whatever autocorrelations you capture, okay, you will have through correlations also. All things come, okay. So what I want to say is, even if you take AR1, you will have some correlation with this one, through this one, okay. No direct, because direct means I have to write another term, beta xt minus 2. Then there will be a direct correlation. But here there is no direct correlation. Through T minus 1 you have a correlation. Direct correlation 0. Let me draw the diagram this way better. So you have direct correlation in AR1, and we have through AR1 we have a link between T and T minus 2, okay. And if you continue, you will have links continuing. You have correlations, okay. You can find rho 1, rho 2, rho 3, rho 4, it will continue. But ideally, when you are considering a stationary process, there should be something, okay. Now I will show you one AR1. This is autocorrelation function of AR1. I will show you the graph also, R coding graph. So if you see, it's continuously decreasing. If you see this one, autocorrelation of AR1, it's continuously decreasing. Okay, so that is what you can mark. It's decreasing, geometrical decreasing we say, but we have, it's not completely zero, right? It's not completely zero. What I want to say is, this is there. I mean, if you take 0.7, if I write this way, xt is equal to, this is the example, 0.7 xt minus 1 plus it. If you remember, if you find directly, you will get alpha. We have solved this problem also with alpha. If you remember, we found rho 1, okay, and we got alpha. Alpha is 0.7. We found rho 2, that was alpha square. You go and verify. 0.7 square, 0.49. Okay, you see here 0.5. This is 0.49, and this is 0.7, and this was alpha 3, alpha power 3, 0.7 power 3. Okay, you find here, you will get this one, this height. Okay, this height. So the correlations, they decrease geometrically here. But if you find partial autocorrelation, you have only one. Partial autocorrelation is the direct correlation. Okay, now when I write this one, AR1, and if I write T here, T minus 1 here, T minus 2 here, what will happen? What is the direct correlation between this and this? That means you directly see the equation and you say, is there a link directly between T and T minus 2? No. Only there is a through correlation. I am talking about AR1. I am not talking about ARP. In AR1, these are the graphs of AR1. Yeah, it's written here. Graphs of AR1. So if you see AR1, you will have only one, and that is equal to, the notation is phi 1 here. Phi 1 is equal to rho 1. Phi 1 and rho 1, they are equal. Okay. Because what is the correlation between, whatever is the direct relation between T to T minus 1, that is the direct relation between T to T minus 1 when we find partial autocorrelation. So we find only direct correlation. We don't include those indirect correlations. So you can relate this way. Suppose, again, there are three friends. Okay, there are three guys. A knows B and B knows C, and once A and B, they were talking. A says, I know C also, but not that well. Okay, so if you find the link between A and B, they will sit together. A might have more relation with C. Through B, there will be some relation. Okay, or maybe in terms of you can say the book sharing, because A and B, they share their books, B and C, they share their books. So if they get together, when A and C, they get together, okay, A and C, they know themselves, suppose, and they can share some books together, and B has given some books to C. So that way also you will get more books from C. That way the association, we talk about the association. Okay, when you find direct link with A to C without considering the impact of B, then we talk about partial autocorrelation. That is what you need to remember. Okay, now let's come here, this graph. Let's come to this graph. When we talk about this graph, we found the correlation. Suppose this is our 0. This is a very important one. This is time 0. Okay, now when we say this is the correlation graph, this is 1. That means you have to know how to find autocorrelation. Suppose this is 0, this is 1 upon 12, 2 upon 12, 3 upon 12, that way. Now successive month, suppose you consider the time series, you consider this time series, okay, and you record the temperature, monthly temperature. So what will happen if I write this way, x1, okay, x1, x0 value, then x1 upon 12 value, x2 upon 12 value. These values when I write, January, suppose this is January, February, March, April, Okay, that will give you row 1. Row 1 means what? The link between the temperatures January, February, February, March, March, April, April, May, that way. Row 2 means x0, x2 upon 12. This way. You see between these two, this. This is row 2. Okay. 0, 2, 1, 3, then 2, 4, 3, 5. This way you have to check with 2 lag autocorrelation. Now, this graph, if you find the autocorrelations, you will see the autocorrelations. Also, you see the autocorrelation. The autocorrelation between January, January, February, February, March, March, 100%. Now, 1 lag autocorrelation means what? 1 lag autocorrelation means actually this is the autocorrelation. This line, you see this line. This is the autocorrelation. That means this will be less. January, February, February, March. See, it's a stochastic process. When I talk about a stochastic process, you have to consider all. Even when I write this, when I write a simple relation like this, xt is equal to alpha xt minus 1 et, that means if you put t10, 10, 9, 9, 8, 8, 7, all we are considering. Okay. So when I say this one, the autocorrelation between January, February, February, March, March, April, April, May, that way. Now you go to this one, 2 lag autocorrelation, 2 lag autocorrelation, 3 lag autocorrelation, like that you find. Okay. You see that if you go to 6 months here, they will be negatively correlated. Okay. That means you consider January and June or July, whatever. Okay. So if you see they are negatively correlated, you need to join here. The correlation is negative here, -1. Okay. That means they are totally opposite. And when you come back once again to slowly this way, when you come back to this one, again it will be 0. Okay, 0. When it will be 0? Sorry, I was talking about 1. When it will be 0? When it will be 0, that is what you need to know. So now here it will be 0, and then again when this is 12 months. Okay, remember this is 12-month correlation. Now here it will be 0. When it will be 0 means what you will answer? 6 months here, not here. Here there is still some negative. Here there is negative correlation. Here 100%, one row is 1. Here little bit less, here less. It's like 3-month correlation. Okay, January, this is January, January, this is January, February, February, March, March, April. This is January, March, February, April, March, May, that way. 2 month, 3 month, that way. If you come to 6 months, it will be -1. Okay, if this is 1, this is -1. Again the correlation will increase. Again the correlation will increase, and when you go to this one correlation will be 1. Okay, so with lag, if you take lag with 12 months here, 12 months means what? This way, 2021 January, 2022 February. Okay, 2023 January, 2023 January, 2024 January. So if you see this one, you take 2021 January to 2022 January. Okay, so if you see this way, there is 100% once again correlation, though there will be little bit change, but January, January, December, December, that way if you see. So with 12-month lag, you will have a high correlation once again. So it's fluctuating. Okay, this is not a stationary time series. Because it will decrease, you think that they are decreasing, the correlations are decreasing, ultimately it will go to 0. That is the property of stationarity. There will be no past dependency, but you will see that again the correlation comes. Okay, so the correlation will decrease, it will go to 0. Even in this case it will go to negative, again it will come back to 0, again it will be 1. So this continues. Okay, we have different seasons. This is not stationary, but you have to know what are the autocorrelations through this example. This is from your material, okay, you can check. This is one of the question, solution to one of the question. Now if I come back here, this is over, then let me go to MA1, okay. If I write MA1, you see the opposite thing. If you come to MA1 process, in MA1 process, if you write xt, that will be equal to et plus beta et minus 1. So here fortunately mathematically also we proved it, we found, we got rho 1, okay. Here in MA1 process we got rho 1, and from rho 2 it was 0. Maybe it was beta divided by 1 plus beta square if I remember, and rho 2, rho 3, rho 4 all are 0. All are 0. Here beta, if beta is 0.7, okay. So 0.7 divided by 1.49. This is what you get here, rho 1, okay. But from rho 2, rho 3, rho 4, everything will be 0, the autocorrelation function, okay. Suppose you get a time series, you draw and you graph, you see the graphs, and you know that you have only one autocorrelation here and all are 0. Again, when you consider sample, maybe you will have small positive, negative and all that. You might consider 0, and also we'll see when one autocorrelation should be considered 0, what length will start considering 0. Those things will go to later. But remember, I am talking about population autocorrelation. In sample autocorrelation, exact 0 you might not get, okay. But this is the property. Like I say, if you toss a coin, you might get 50 heads, that is population, right? So these are the property population autocorrelations. I am talking about population autocorrelations. All are 0 exactly here, population autocorrelations, okay. But here partial autocorrelation will continue, that will not be 0. Now go here, go to AR1. Autocorrelations will continue, but the partial autocorrelation will be 0. So it's very easy for you now. You draw, you find the correlations, you find autocorrelations, okay. If your autocorrelation becomes 0 after one step, you are sure that it's from AR1 process. If partial autocorrelation will be 0 after step 1, then it will be AR1. If partial autocorrelations will become 0 after step 2, it will be AR2. Suppose you get this way, you have 2, but from 3 it's 0, okay. You have 2, but from 3 it's 0. Then it will be from AR2. You need not see this one, okay. Directly if it becomes 0. Suppose we have 3 partial autocorrelations, from 4 it's 0, AR3, that way. Similarly, if it's a pure MA process, here you have one autocorrelation. Suppose you have 2 autocorrelations, okay. Then 0. Then you can say that it's from MA2 process. You can apply MA2 process to predict. And after 3 it's 0, then fine. But suppose you have all here not becoming 0, or they are increasing, like I showed you, one increasing, decreasing and all that, their behaviors, okay, they are not decreasing, then you need to consider ARMA process combination. And also we'll think about how they are decreasing, whether there is a steady decrease or not. All those things will come later. But now at this level, you should be able to recognize the pure processes from the graphs, at least ARP or MAQ, pure process. Pure means if it's MA1, MA2, MA3, you will be able to check. If it's ARP, AR1, AR2, AR3, you will be able to check, okay. So if you find partial autocorrelation, suppose I say that this is AR3, pure AR3, partial autocorrelations from 4th should be 0. All others should be 0. This is what you need to remember. Now, if autocorrelations you find, and you want to say it's MA3, make it sure that your row 4, row 5, row 6 all should be 0 with non-zero row 1, row 2, row 3. Okay, here also phi 1, phi 2, phi 3, they will be non-zero. There will be some amounts. So pure processes you will be able to understand. However, if there is a mix up, those things we'll do separately. Also there is a deterministic effect and all that. We'll go to those things later. Now, how to find partial autocorrelations from autocorrelations? As I mentioned you before, you won't get partial autocorrelations directly. Suppose I have link with someone. I have link with my wife's sister. Okay, me, then I have some relation, okay, through my wife, I can say this way. All right. So, but if you find the direct relation here, that is not, okay, that is not. Only through wife there is a direct relation. So what I am saying is, how can you extract, suppose you have this much water now, and you want to extract, you want to estimate what is the amount of water, okay, that is due to today, that you can only estimate. That estimation is there, that's again another class, that is not there in our course, will not worry. Okay, there were a few lines before, 2 to 3 theoretical definition if you want understand, but conceptually if you want to understand, okay, you need to estimate partial autocorrelations. Now, how to estimate partial autocorrelations? I'll tell you. Phi 1 is equal to rho 1. Phi 2 when I write, this is the numerator, okay, denominator. 1 rho 1 row 2, replace first row by row 1 row 2. Now when you find phi 3 here, you can remember this way easily. This is phi 2. You can remember this way, phi 2 is equal to this, phi 3 is equal to this. See, I will write now. I will copy row 1, 1, row 1, row 2, row 1, 1. The first row I will replace by row 1, row 2, row 3. This way you can write phi 2, phi 3, phi 4, phi 5, whatever. Now I will show you everything, whatever I taught. We started with this one, autocorrelation for ARMA. Also I will show you something more. This I discussed in the last class, time series, if you remember. Autocovariance, autocorrelation, okay. Autocovariance, you are estimating from sample. Sample will not get in the form of row. Remember, row are only estimated. This is also an estimation, okay. So mu is estimated and the gamma case are estimated, then rho case are estimated this way. Once you estimate this one, then the estimate of this one, you divide, you will get this one, okay. This I discussed in the last class. Now here if you see autocorrelation function for ARMA 11, xt you write this way and you find rho k this way, okay. This is what we have done today in today's class. I started with this one, ARMA 11, and I think we find rho 1 if you put k1 here, alpha 01, and I found gamma 1, okay. You have to divide by gamma naught to get rho 1. And this one, even I think this one is given in your material, one example. That is what I discussed in today's class. And partial autocorrelation function, you need to find this way. Gamma phi 1 is rho 1, phi 2 is rho 2 minus rho 1 square divided by 1 minus rho 1 square. Phi k is equal to this given, but yeah, you can directly see how it is. 1 row 2, you continue. Here also you continue. Row wise, column wise, you complete first row, first column, then go to the first entry of second row, second column. You start with 1, again complete this, complete the row and column, then go to the third entry, that is third row, third column. You write 1 here, complete the row and column, okay. This way you can remember. Suppose you get a question, xt is equal to 5 upon 6 xt minus 1 minus 1 upon 6 xt minus 2 plus ct. The question was find we have done this one already. Part was find phi k. Okay, now this part you will be able to do. Remember, this always will try to find from this one. Okay, so if you know row naught, if you know row 1, if you know row 2, then you can find phi 1, phi 2, phi 3. Okay, considering that this is AR2, this is a AR2 process, you can directly write phi 3 0. Considering that this is AR2, you can write phi 3 0, and phi 1 for phi 1, phi 2 you have formula. Okay, you can use that formula. That is again row 1, whatever you get you write here. And for this one you can write always this way: 1 row 1 row 2, and here it will be, you have to start with 1, then this is over. This is one part only. Let me write phi 2 here. This is the denominator: 1 row 1 row 1, there is nothing, and you copy this and replace the first row by row 1 row 2. That's all. So using this formula you can find phi 2. I think it's 1 minus row 1 square. This should be row 2. This is row 1 minus row 1 row 2. Okay, so you just put the values of these and you find, sorry, this is a, you find these things. This should be 1, right? So this much you need to do. Okay, class is over for today.